So in this section, we're going to look at how the resistance of a resistor depends on temperature. So let's look at dependence of the resistance of a resistor on temperature. Now, as you've seen in the previous section for a wire, you see, remember this formula, resistance of a wire equals resistivity times the length divided by the cross-sectional area. So for a given length and cross-sectional area of a wire, resistance is actually proportional to resistivity. So that tells us that resistance depends on temperature the same way as resistivity depends on temperature. Okay, so we have the following relationships. Resistance, it is, let's say resistance okay, so change in resistance is proportional to change in temperature. Change in temperature is also proportional to the initial resistance. Proportional to the initial, that is before the change in temperature, initial resistance. Okay, mathematically we can write this as the change in resistance is proportional to the initial resistance and proportional to change in temperature. So of course mathematically this means the ratio between the change in resistance and the product of initial resistance and change in temperature is a constant. This is the same constant for resistivity. It's called coefficient, temperature coefficient of resistivity. Temperature coefficient of resistivity, and we're going to use alpha. Okay, so we have delta R divided by R naught delta T equals alpha, or the change in resistance equals initial resistivity alpha times delta T. Okay, so this is a formula that relates change in resistance with change in temperature. Now this formula is useful if you're dealing with changes. You calculate the change in resistance corresponding to a certain change in temperature, but sometimes you might be looking for the resistance at a particular temperature. So let's modify this formula in that case. So we can write delta R as resistance at temperature T minus the initial resistance, and delta T would be the final temperature minus the initial temperature. Okay, so with that we're going to have delta R equals R minus R naught, and then we have alpha R naught, and change temperature is T minus the initial temperature. Okay, so if you take the initial resistance to the other side, we have this equals R naught plus alpha R naught, and then change in temperature. Okay, now we can factor out the initial resistance, so we have resistance at temperature T equals initial resistance 1 plus alpha, and then change in temperature T minus T naught. Okay, so if you're interested in the resistance at a particular temperature, you can use this formula. Okay, now let's consider an example. Okay, a resistor whose resistance at 20 degrees centigrade is let's say 40 ohms, is connected, let's say, to potential difference of 10 volts. Now calculate the current in the circuit when the resistor, let's say, is heated to a temperature of 120 degrees centigrade. Okay, so with the other page. So we have a battery connected to a resistor. Okay, the potential difference of produced by this battery, that's delta V, is 10 volts. Okay, now this resistance has a value of 40 ohms at temperature of 20 degrees centigrade. Okay, so R20 is 40 ohms. This is resistance at 20 degrees centigrade. Resistance at 20 degrees centigrade. Now the temperature of the resistor is increased to 120 degrees centigrade. Okay, and we want to find the current flowing through it at a temperature of 120 degrees centigrade. So we're looking for the temperature for the current at a temperature of 100 degrees centigrade. Okay, so the question is to find this one. Okay, so we can say the current at 120 degrees centigrade equals the potential difference divided by the resistance at 100 degrees centigrade, 120 degrees centigrade. But we know the resistance at 20 degrees centigrade. So first we have to calculate the resistance at 120 degrees centigrade. Okay, and let's assume the value of alpha. Alpha, let's say, is 3 times 10 to the power negative 3 per degree centigrade. Okay, so we have the following formula: R at 120 equals R20, that's initial, 1 plus alpha, and then the final temperature 120 minus initial temperature 20. Okay, this is the final temperature, the initial temperature, and R20 is 40. So you get this is 40, 1 plus, and this is 3 times 10 to the power of negative 3, and then of course this is 100. Alright, so we have this 40 times, you see it's 10 to the power negative 1, so times 1.3. Okay, so this is 52 ohms. Alright, so the resistance at 120 degrees centigrade is 52 ohms. Therefore we come to this formula over here. The current at 120 degrees centigrade is the potential difference divided by the resistance at 120 degrees centigrade, and the potential difference is 10, and the resistance at 120 degrees centigrade is 52. Okay, that is amps, or 5/26 amps. Now we're going to talk about power. In the resistor, we're talking about the rate of dissipation of electrical energy in a resistor. That is rate of dissipation of energy in a resistor. This is rate of dissipation of electrical energy in a resistor. So remember, a resistor is a device that converts electrical energy to non-electrical energy. So you can say this is rate of conversion of electrical energy to non-electrical energy. This is basically rate of conversion of electrical to non-electrical energy, So that's what power resistor is, a process of conversion of electrical energy to non-electrical energy. So power is rate of conversion of electrical energy to non-electrical energy. Now, if you remember the general definition of power is rate of doing work or rate of conversion of energy. You can say power is rate of doing work or rate of conversion of energy. Okay? So power, if you use P for power, is basically the work divided by time or energy divided by time. Okay? This will be the definition of power. And the unit of power, as you can see from here, unit of power is the unit of energy, which is joule, divided by the unit of time, which is second. This is defined to be watt, and we're going to use capital W to represent it. Okay, so the unit of power is watt, which is joule per second, and it's going to be abbreviated by capital W. Okay, now we're talking about a resistor. So let's say we have this resistor over here. So the charge goes from here to here. It loses potential energy delta U. Okay, and if you remember, this change in potential energy of the charge equals charge times change in potential difference between these two parts, right? So this is the change in energy or energy converted in time interval t. So we can say that the power in this case for resistor is a change in potential energy delta U divided by time. Okay, but this change in potential energy is charge times potential difference between the endpoints of the resistor divided by time. But remember, this over here is the rate of flow of charge, which is current. Okay, but Q over T equals current. Okay, so we have the following formula for power. So the rate of conversion of energy in a resistor equals current times potential difference. So that's how we calculate the rate of dissipation of electrical energy in a resistor. Okay. Now, using Ohm's law, we can obtain alternate formulas. For example, if I replace delta V by current times resistance, I'll get the following formula. Power equals current times R, and that gives me another alternative formula, current squared times resistance. Okay, so I can use this formula if I know the current and the resistance. Or if I decide to replace current by potential difference divided by resistance, then I'll get the following formula, delta V over R times delta V. So I get the formula power equals the square of potential difference divided by resistance. Okay, so depending on what you know, you can use one of these formulas to calculate the rate of dissipation of energy. All right, example. let's say a 10 ohm resistor is connected to a 6-volt battery. Okay, so the question is, calculate the rate of dissipation of energy. Dissipation of energy in the resistor. That is the rate at which electrical energy is being converted in something else, usually to heat energy. All right, so what do we know? We have the following situation. This is a battery connected to a resistor. We're told the resistance is 10 ohms and the potential difference is 6 volts. Okay, so being asked to calculate power. Okay, so we know potential difference and resistance. So in this case, we know potential difference and resistance, so this would be the best formula to use. Okay, so we're going to use power equals delta V squared divided by resistance. All right, so that will be 6 squared divided by 10, and that is 3.6 watts. Okay, now let's say calculate the energy dissipated let's say in maybe 10 hours. Okay, so we have the power is 3.6 watts. Now we want to find the amount of energy dissipated in 10 hours. Okay, remember power is energy divided by time, so we're being asked for energy in this case, and so energy is power times time. Okay, so this is in hours, but in SI units we have to convert it to seconds. So the time is 10 hours, but that is 10 times 60 minutes times 60 seconds. Okay, so that is 3600 times 10, which is 36,000 seconds. Okay, therefore the energy dissipated or converted to something else, for example, if it's a light bulb, this is the amount of energy we'll get in 10 hours. Okay, so the energy is power times time, and then we have the power is 3.6, and the time is let's say 3.6 times 10 to the power of 4. Okay, so this would be 3.6 squared times 10 to the power of 4, and that is joules. So this is how much energy you get in 10 hours. All right, now we're going to find a unit of energy commonly used by the power companies. It's called kilowatt hour. So let's define the unit of energy called kilowatt hour. This is the unit of energy, and it's equal to the amount of energy dissipated by a 1 kilowatt device when used for an hour. This is equal to the amount of energy dissipated or converted to something else when a 1 kilowatt device is used for 1 hour. 1 hour. Okay. All right. So let's convert into joules. All right. So we know that energy is power times time. Okay. So kilowatt hour, according to this definition, okay, it is power times time. The power of the device is 1 kilowatt or 1000 watts. Okay. And it's used by 1 hour, which is 3660 times 60. Okay. Times 10 to the power of 3000. Okay. So you see that this is watt, this is seconds, therefore we get joules, right? So 1 kilowatt hour is equal to 3.6 times 10 to the power of 6 joules. Or let's just abbreviate this by kWh, okay? Abbreviation for kilowatt hour. So we have 1 kilowatt hour is equal to 3.6 million joules, okay? So if you ever look at your electric bills, you will see that they measure the energy in kilowatt hours, and that's what this means. 1 kilowatt hour is 3.6 times 10 to the power of 6. 3.6 times 10 to the power of 6 joules. All right. Now let's consider an example. Let's say, suppose the cost of electricity is, let's say, 10 cents per kilowatt hour. Per kilowatt hour. Okay. Calculate the cost of using a 100-watt lamp. Let's say use it for 10 hours. Okay. So we have a lamp that has been used for 10 hours and its power is 100 watt. That is, it dissipates 100 joules per second. So if the cost is 10 cents per kilowatt hour, we want to calculate how much it costs us to use this device. Okay. So let's look at the solution. So the cost is 10 cents per kilowatt hour. Okay. Or let's say the price. This is the price. The price is 10 cents per kilowatt hour. Okay. So the cost would be, you would multiply the price by the energy in kilowatt hours. Okay. Energy in kilowatt hour. That would be the cost. For example, if you use 2 kilowatt hours, then the cost between cents. If you use 3 kilowatt, and so on. Okay, so you have to multiply the price by the energy in kilowatt hour. So that's what we have to obtain. We have to obtain the energy in kilowatt hour and then use this formula. Okay, so what do we have? We know the power is 100 watt. Okay, or we can say this is 0.1 kilowatt. Let's see, divided by 1000 to change it to kilo. Okay, and the time is 10 hours, right? So the energy is the power 0.1 kilowatt used by 10 hours. Okay, so that is, wow, that's just 1 kilowatt hour. Okay, so the cost is price, which is 10 cents per kilowatt hour, and then the energy user is simply one kilowatt hour. Okay, so that costs 10 cents in this case. Okay, it's just 10 cents because the device used just 1 kilowatt hour in 10 hours.